So this presentation is a review of some of the things you learned in Calculus 1. We're not going to be able to go over everything from the first semester of calculus, but we are going to be able to hit some of the highlights, review some of the definitions, some of the formulas that you'll need to know for Calculus 2. So one of the first things we talked about in Cal 1 were average rates of change for a function. So the idea is that if you have a function over an interval a to b, then the average rate of change will be f of b minus f of a over b minus a. So what we have is a quotient of two differences. In the numerator, we have the difference of function values, and in the denominator, the difference in x values. And for that reason, we often call this a difference quotient. The units for an average rate of change are always the units for your function f over the units for the variable x. So as an example, if f was position and the units were meters, and if x was our variable and it represented time in seconds, then the average rate of change would always have the units for average velocity, or meters per second. Now in calculus, we talk about not just average rates of change, but instantaneous rates of change. In other words, the rate of change at a particular point, at a single point, not over an interval. The instantaneous rate of change is defined to be a limit of average rates of change over an interval a to a plus h, where we let h go to 0. So our instantaneous rate of change is the limit, as h goes to 0, of f of a plus h minus f of a, and then the denominator simplifies to just h. Another way of describing the instantaneous rate of change is to call it the derivative of the function. So we can use a couple of different notations. On the left here, this dy dx notation is known as Leibniz notation. And then the prime notation, f prime of a, is a notation we get from Newton. They mean the same thing. The limit as h goes to 0 of f of a plus h minus f of a all over h. So the units for f prime are the same as the units for the average rate of change. Those are the units for f divided by the units for the variable. So derivatives can give us information about a function. So the first derivative, for example, can tell us whether a function is increasing or decreasing. Positive first derivative means increasing function. Negative first derivative means decreasing function. If we look at second derivatives, that tells us about how the function's graph bends, or what we call the concavity. So if we have a positive second derivative, then that means the first derivative was increasing, and so we have a graph that's concave up. On the other hand, a negative second derivative means a decreasing first derivative. That means the function is concave down. Combining information about the first and second derivatives gives us four basic shapes for a graph for f. Any particular place in the graph will either be, as in the first case here, increasing but concave down. The second one is increasing but concave up. The third shape is decreasing but concave up. And the final shape is decreasing but concave down. We sometimes think of concave up as a shape that would hold water and concave down as a shape that would not. And it's also useful to connect the idea of the function's derivative increasing or decreasing to the concavity. If we look here, if I draw a tangent line to the function graph, notice how the tangent lines are getting less and less steep as we move to the right. So that means the slopes of the tangent lines are decreasing. That means f prime is decreasing, and that results in a concave down shape. On the other hand, concave up means that these tangent lines are increasing in steepness as we move from left to right. So an increasing derivative means concave up. Here is a useful applet that if you open the PowerPoint presentation, you can sort of play with this on your own, and it's a way of visualizing the derivative of a function. So the derivative of a function is the slope of the tangent line, and the difference quotients represent slopes of secant lines. So as we let h go to 0, which I can do with this slider, we see the points A and B coalesce, and as they do, we get a tangent line to the graph, one that touches only at one point, as opposed to a secant line which goes through 2 points. So we can go kind of back and forth, seeing secant lines approaching the tangent line from either side. This next applet allows us to see what the graph of the derivative would look like based on the graph of the function. So this one's interesting in that if we slide the white dot, we have to go kind of slow sometimes, but what we can notice happening is the derivative, as we move from left to right, is increasing. It's getting steeper and steeper. That checks out with the concavity of this graph being positive. And the applet also shows us where we have negative derivatives, which represent negatively sloped tangent lines here on the left, versus positive derivatives, which represent positively sloped tangent lines that we get on the right-hand side. And notice right in the middle, right at 0, we would get a 0 slope for a horizontal tangent line, and that's where the derivative changes from negative to positive. So we developed several rules for finding derivatives in Cal 1. First off, the derivative of a constant times a function is just the constant times the derivative of the function. The derivative of a sum or difference is the sum or difference of the derivatives. The derivative of a power becomes n times x to the n minus 1. So you bring the power down front and decrease it by 1. Product rule. So the derivative of f times g is the derivative of the first here times the second plus the first times the derivative of the second. The quotient rule. We get the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And then finally the chain rule, which is often one of the hardest to get used to. If you have the derivative of a composition of functions, you get the derivative of the outside function evaluated at the inside times the derivative of the inside function. Along with our derivative rules, we have several common derivatives that we just have to commit to memory. The derivative of a constant is 0. The derivative of x is just 1. That's really a special case of the power rule, but it's helpful not to have to use that. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of e to the x is itself. Derivative of a to the x is the natural log of the base times a to the x. Derivative of natural log is 1 over x. Our first example is an application of the product rule. We have to find the derivative of x to the 10th times e to the x. So the product rule tells us that derivative will be the derivative of the first. So the derivative of x to the 10th times the second, which is e to the x, plus the first, x to the 10th, times the derivative of the second. So now we use our power rule to figure out the derivative of x to the 10th. That's 10x to the 9th. That's times e to the x plus x to the 10th. And now we have to remember the derivative of e to the x is just itself. So our final answer here is 10x to the 9th times e to the x plus x to the 10th times e to the x. We could factor out an e to the x, but it's not necessary. For our next example, we have to use the quotient rule, which tells us that the derivative of a quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And all of that is over the square of the denominator. So if I take the derivatives on top, I get the derivative of log x is 1 over x plus the derivative of sine x, which is cosine x, still multiplied by x squared plus 1. And now I subtract log x plus sine x and multiply by the derivative of x squared plus 1. Derivative of x squared is 2x. The derivative of the constant 1 is 0. That still remains over the denominator squared. And even though we could probably do some factoring or simplifying, this form will suffice. Finally, we have an application of the chain rule, although it's actually got both the product rule and the chain rule in it. So we're finding the derivative of x times the cosine of x squared plus sine x. First is the product rule, the derivative of the first times the second plus the first times the derivative of the second. So we have to execute each of those individual derivatives. The derivative of x is just 1. So I get 1 times cosine of x squared plus sine x plus x times the derivative of cosine of x squared plus sine x. So this is going to be an application of the chain rule where the inside function is x squared plus sine x, and the outside function is cosine. So by the chain rule, I need to find the derivative of the outside function, which is minus sine, evaluated at the inside function, all times the derivative of the inside function. So the derivative of x squared is 2x, and the derivative of sine is cosine. So it's kind of a mess. That is something we might be able to simplify a little bit. But again, for just reviewing derivative rules, this will suffice. So as a reminder, we spent a fair amount of time in Cal 1 on applications of derivatives. One of the big topics was optimization, where you're finding maxes and mins. And then related rates, where there is generally some unknown rate that you're interested in. It might be hard to measure, but you know it's related in some way by the Pythagorean theorem or similar triangles or something like that to a rate that you do know. So after derivatives near the end of the term, we discussed what's called the Riemann integral. And this is a quick version of that definition. You have a continuous function on some interval a to b. We partition the interval into lots of smaller subintervals. The width of each is what we call delta xi. If we're using equal subintervals, that ends up being b minus a divided by n. From every subinterval, we select some point that we call C sub I, sometimes called a test value or test point. But we often also just go ahead and take the right-hand endpoint, x sub I, sometimes the left and sometimes the midpoint, but often the right-hand endpoint. If we take f of xi, that represents the height of the ith rectangle. That sits above the ith subinterval. And then f of xi times delta xi, that would be height times width. So that represents the area of one of those rectangles. If we add up all the areas of the rectangles, then what we get is a good approximation for the area under our curve, f of x, as long as we've taken enough rectangles. So generally speaking, the more rectangles we take, the better. So that motivates the definition of our Riemann integral. So we can see this definition in action in the next applet. So this is set up, it's got a graph of the function 1/2 x squared plus 1. We can change that if we'd like, but for now we'll leave it. And the limits for finding the area go from -2 to 3. Now to start off with, we've split the area up into 3 rectangles, and notice that whether we're using the upper sum or the lower sum, we've got quite a bit of error in that estimate. So the way we fix that is we take more rectangles. So here's 12 rectangles. Notice how the error involved, the difference between the rectangles, either the large rectangles or the small ones, and the area under the curve is getting smaller. With 30 rectangles, we're doing a pretty good job of approximating the area under the curve. And then as we increase the number of rectangles, we do better and better and better, until with 100 rectangles, we're within a couple of tenths of the actual area. So our upper sum, the large rectangles go to about 11, the true area is about 10.8, and then the lower rectangles are about 10.7. A difference that it's hard to even really see in the graph. Now, using that definition, we can evaluate some Riemann integrals. If you remember doing that in Cal 1, that involves summation formulas and limits that can sometimes be really messy. So that's not generally the way we'd like to do it. Instead, we use what's called the fundamental theorem of calculus. And that theorem says that if we know a function whose derivative is little f, then the integral of little f is actually much easier than finding a limit of sums of rectangles. It's just that function capital F evaluated at b minus capital F of a. So it's a much, much better way to go if you can find a function capital F whose derivative is little f. Much of what we're going to do in Cal 2 in the first part of the term is developing ways of finding that capital F. As a second example, we have an application of the fundamental theorem of calculus, just to remind us how that works. So in this example, we have to find a definite integral. So one way to interpret the integral is we are finding the area under the function 3x squared between the points x equals 1 and x equals 3. Now, you might remember that we can find this area using the definition of the Riemann integral, but those are generally pretty hard and get pretty messy. So when possible, we like to use the fundamental theorem of calculus. So to use the fundamental theorem, we have to figure out some function we usually call capital F of x, whose derivative, capital F prime, is in this case 3x squared, whatever function we're trying to integrate. Thinking about the power rule, we can make a pretty good first guess for what capital F of x should be. Let's try x cubed. So with that as our capital F, f prime by the power rule would be 3x to the 3 minus 1, which is 3x squared. So let's remember what the fundamental theorem of calculus says. If we have to find the integral from a to b of some function, little f, then that's the same as an antiderivative for little f evaluated between a and b. In other words, capital F of b minus capital F of a. So we have found the capital F in this case. So all that remains is to plug it in using the fundamental theorem. So I need to evaluate x cubed from 1 to 3. And when I do that, I get 3 cubed minus 1 cubed. That's the same as 27 minus 1. And so our final area, without having to do any rectangles or limits or anything like that, is 26. So when we meet again, we'll be able to resolve any questions remaining about the presentation, any of the material or examples in that presentation, and we'll have some problems to work on together to try to reinforce the concepts and techniques in that lesson. So I'll see you next time.